All right, we're going to talk about distributions tonight. I'm just going to gloss right all over that. Uh, so, um, where to begin? So, we're going to revisit our good old coin toss example. So, just to remember, last week we were talking about this notion, right? Law of large numbers. We're talking about full probability distributions, all that kind of stuff. And right. And so I was looking at this one example where this is essentially a cumulative sum plot, right? So the way to think of it is like if you get a heads, you add one. If you get tails, you subtract one. And so over the long run, right, we would expect that cumulative sum to be around zero. Of course, we're never, we expect because of random chance that we might deviate away from zero. And as we alluded to, a big part of this class is like, well, how far, in this example, let's be concrete here. How far away from zero would we have to be before we'd be like, hmm, I wonder if this coin is not fair. Um, so that's what we're going to look at, right? So here's a single example, right? And in this case, I ended up at positive four, right? And last week we showed one where, okay, well, the range of the y-axis could go from negative 100 to positive 100. If you do that, this line looks a little less, you know, variable, right? It's like just kind of bouncing around zero and you might not even be able to see it. So I'm considering this like one event, right? This is like one sample, if you will, right? We talked about sampling early on. This could be considered like one sample. So the question, and really what I'm interested in is after I flip a coin 100 times, where do I end up, right? So, um, well, in R, we can do this. Like a long time ago, I used to do exercises like this when I used to teach in person. It's like give everybody a coin, flip your coin 50 times and we're going to record and we can collect it all together. But now with R, I can just do this in code. So what am I going to do? I'm going to initialize a vector called samples, and I'm just initializing it to NA and I'm making it 1,000. So if you want to run this later, you can go to 10,000, 100,000, whatever. Don't go too crazy because it's, unless you have a really good computer. Although this runs pretty fast. By the way, as I'll do this as a slight aside. So, in terms of our programming things, um, it's often stated that R is bad at for loops. And that is, or, it's not, but that's only partially true. The reason why R is bad with for loops is it tends to replicate data structures on each iteration, right? It creates new environments on each loop. And R is designed to be, if, don't worry about if this doesn't make sense to you, but it is a vectorized language, right? Which is why it's really great for statistics, is that it's extremely efficient in doing matrix type algebra, if you will. Um, so, anyways, but I like for loops because to me they're a little bit easier to understand. Because essentially what I'm doing here, and some of you are new to programming in R, I'm going to have some looping variable I. So sequence along, essentially, this is just going to create a vector, 1 to 1,000. So on the first pass, it's going to set I equal to 1. It's going to run everything in the curly braces 2, et cetera, et cetera, et cetera. Now, if I concatenated a vector as I built it up, which is what I might do in Java or something, or I'm expanding an array, that's probably, or C, that would be fine. But here, because I'm initializing it and I'm just setting each element, R is not going to allocate new things. So this actually is actually pretty fast. Um, and the other reason why I like for loops is that you can easily make this run in parallel by most of the time you can just there's a package called for each, and you change this for each as long as it's a what they call a simple parallel problem, meaning each iteration of the loop is independent. Then it'll just split it out. You can initialize and say use I have 12 cores on my machine. You can, a lot of times I just say use one minus however many cores I have. So I can have one core to monitor and it doesn't like really freeze my computer. Um, you could do that. So, anyways, I digress. The point of this here is I'm looping through. I'm drawing a random 100 coin. I'm simulating 100 coin tosses, and I'm keeping the last one. right? What does that mean? I do this, and I just want to know where I ended up. Okay. And then here I'm just looking at the first 15. So you can see I had 2, 8, 2, 0, 16, minus 2, 14, et cetera, et cetera, et cetera, et cetera. So now I have a vector, right, of these endpoints of where I end up after flipping a coin, right? Probably, hopefully, intuitively, you think we should be around zero. But what does the shape of this distribution look like? Well, it looks like this, right? So here's a histogram. This should look familiar, right? Hopefully, everybody's kind of heard of the normal distribution. And in fact, it is normal. Now, it does look a little bit bimodal. I probably should have. I didn't set a seed. I think we talked about seeds last week. So every time I generate this slide deck, I get a different picture. So some semesters I have to talk a little bit more, but it should be normal, right? This is simply a random process, and the result is a distribution that looks kind of like this bell shape that we've all heard about. So because I have this vector, I can just ask for the mean and I get 0.522. So I don't actually get zero, but it's pretty close to zero. And the standard deviation is 10.2. So I'm going to round that. Let's just call it 10 so I can do some arithmetic in my head easier than saying 2.2 or 10.25. Okay. So now I want to say, let's explore this a little bit. So I have this vector samples, and what I'm doing on this first one is saying, give me all the observations from the samples vector where the sample is within one standard deviation. So I'm saying samples is greater than mean minus a standard deviation, and samples less than or equal to mean plus a standard deviation. So the result of this line is, of the 1,000, how many are between like minus 10 and 10, right? Because the standard deviation is 10 and the mean is roughly zero. Let's just round it just for, again, for simplicity of arithmetic. So I'm taking the length of that vector divided by the 1,000, right? This is essentially 1,000, and I get 67% of the observations. This line is basically same thing, except I added 2 times. So I'm saying, okay, how many observations fall between minus 20 and plus 20? Well, I get 96.2. And then I go 3 standard deviations and I get 99.7. So why am I doing this? Well, here's the actual formula for the standard normal distribution, sometimes referred to as the Gaussian distribution. It's crazy. We do not expect you to memorize it. If you just Google normal distribution formula, Google will give it to you right away in the upper right-hand corner in the knowledge index. You don't need to memorize it. But this formula gives me this. Now, a couple of things, right? We have, so it's a function, right? But given we have a mu and a sigma, which is basically saying we need to give it a mean and a standard deviation. So there's not really one normal distribution. There's like a class of normal distributions, as we'll see in a moment. Now, this plot I have right here is called the standard normal distribution. So anytime we use the phrase standard normal, all we mean is that it's a normal distribution where the mean is 0 and the standard deviation is 1. And we'll talk about the utility of that. So when we do that, this can be simplified, right? Because that goes away because that's 1. This goes away because that's 0. This just becomes 4 in the denominator over here because, sigma is 1. So, but, you can do this. So if we have this function, right, we could start, I think next week I'll do the crash course in calculus, right? I didn't do it here, right? I'm teaching 3 different sections and we're at like different paces. So I don't think I did a calculus crash course yet. That's next week. But real quick, if you've taken calculus, we're taking integrals. So one thing you should know about this distribution is the area under the curve is 1, which is really convenient because we're interested in probabilities. And when we talk about probabilities, we're talking about things that range between 0 and 1. So if the area under this is 1, right, that we could kind of interpret it that way. So what do I want to do? I want to take the standard normal distribution and I'm going to go, what's the area from minus 1 standard deviation to plus 1 standard deviation, right? So I'm taking that fraction of 1 that goes, and it turns out to be 68%. Well, let's go back to here. What did we get? We got 67.1%. Pretty close. If we go 2 standard deviations, what do we get? 95%, which maybe if you're reading a lot of research papers, should start to ring a bell. It's like, huh, 95%. We talk about p-values of 0.05, right? So 1 minus 0.95 is right. So, okay, two standard deviations. That should, if we go back here, what do we got 96.2 and we get 95. Okay. If we go three standard deviations, we get 99.7, right? And we actually got 99.7, right? Dead on, right? So what does this mean, right? Well, in the case of our coin toss, right? If we flip a coin 100 times, right, we would expect the results to be, between 60, 40 and 50, 50, right? In that range, 68% of the time. But a few times, right, we're going to be within two standard deviations and then, three standard deviations. So when, I kind of ask that question, how far away from zero do we need to be before we're like, maybe this coin isn't fair, right? So you have to set your threshold. If you want to be 95% sure the coin is fair, then you would say anything more than two standard deviations away, I'm going to be, I think this coin is not fair. If you want to be more certain, right? If you're a medical researcher, doing a drug trial, I want to be really sure, then I might go anything more than three standard deviations is when I'm going to say, that coin is, I'm really sure that coin's not fair, right? So that's kind of what we're trying to get to. And so from the normal distribution, right, we can get probabilities, right? So, well, what's the likelihood of ending less than 15? Well, I could call this p-norm function with 15, and in this case, I have to give it a mean. So p-norm by default is going to do the standard normal. So I could just give it and say, well, 92% of the time, I'm going to have 15 or less. Now, the p-norm is always going to return the area to the left. So if I want to know what's the likelihood of having more than 15, well, I could just say 1 minus, right? Because as I said, the area under the whole curve is 1. So if we get the area to the left, the area to the right is 1 minus the area to the left. And that's what we get, right? Um, so, right. And so I'm going to talk a little bit more about this, I think, next week, this plot, but I'll just introduce it now because I think it's worth talking about this more than once. And I'll publish this Shiny app before next week. The function to generate this is already in the Visual Stats package, but the Shiny app is new, and the Shiny app and the function that I'm going to update will work with, any built-in distribution in R. But what this is doing here, and right, I'm looking at this p-norm function here. But let's start here. So when you pick a distribution, you can give it a mean and a standard deviation. So if I want to change this to, I could say 0 and 10, which is kind of close to what we have, but then my x min and x max. So let me do, no, 0 wouldn't be good. Let's go, let's say 20 to 80. I think that should be good. Nope, that's really bad because the mean is 0, right? I should say minus 30 to 30. There we go. All right. So, we can tweak this stuff here in the app. But now that I did that, I kind of don't. I want to go back to the I want to go back to the standard norm. And so I need to make that 1. Okay. So here's the standard normal distribution. R for every distribution that function that is there has 4 functions. Okay. D, R, P, and Q, right? So these are the 4 functions. And then after that function is the distribution type. So here I'm picking normal. In a few minutes, we're going to talk about the binomial distribution. So it's binom. So I have a D binom and R binom, P, Q, right? But let me go back to the normal. So for each of these functions, right? So the D is short for density. Another way to think of it, that's f of x, right? If I go back to that function, I'm going to, so the way this figure is designed, the dots are the input to the function and the arrows are the output, right? So the D function is just going to give me the height at that particular part. The R is random, so you notice there's no dots. It's just going to give me random values, however many I ask for from that distribution. So if you want to simulate data from a normal distribution, you can do that. Okay. The P function is going to give me the area under the curve, as I was just showing. Oops, here, right? Now, but what I've done on the bottom two plots is these are what are called cumulative density functions, right? So essentially, I'm just, as I go left to right, this is representing the area to the left from this plot. So you can kind of imagine as I'm going left to right, I'm just taking the area, all the area from, well, what's the height, at -2? Well, it's the area under the curve from -2 to minus infinity. When you get to zero, what is the zero value here? Well, it's 50%, right? Which makes sense. We're right in the center. We have half the area to the left, half the area right. So that's how we read this off. It's still the same thing, right? We're getting the area to the left. So the P is like given how, my standard deviation units, right? Where am I? What's the area under the curve to the left? The Q just goes the other way. I know the area. What's the critical value? Um, and so that's kind of how that works. And we'll look at that again. All right. So now that we kind of have this sense of a normal distribution and, particularly the 68, 95, 99 percent rule, right? That's a property that kind of holds about the normal distribution. This becomes a very useful tool. So let's say, for example, you're a college admissions counselor and you have one more spot and you've got two students who are equivalent on everything except we have Pam who sent her in her SAT scores, and we have Jim who sent in his ACT scores. So really briefly, you just need to know that if you're not familiar in the United States crazy system, SAT and ACT are both designed to kind of measure college readiness, or at least academically. So they trying to measure the same thing, they just do it in a slightly different way. Such that like the SAT is designed where it has a mean of 1500 and a standard deviation of 300, whereas the ACT has a mean of 21 and a standard deviation of 5. So they're scaled differently, but they're trying to measure the same thing. Well, it turns out we can actually convert things, right? We can take any distribution and actually convert it to a standard normal distribution. And when we do that, we call it a z-score, right? Essentially, we're just doing a linear transformation to take a distribution that has a mean and standard deviation. We want to make it have a mean of 0 and a standard deviation. So all we do is we take the observation minus the mean over the standard deviation. The result of that is a normal distribution. Great. So now we can leverage this as a way to kind of put these two scores on the same metric. So if we convert Pam's score, right, she gets a z-score of 1. And what does that really mean? That means Pam scored 1 standard deviation above the mean, right? Jim scored 0.6 standard deviations above the mean. So if you were to pick one, you would pick Pam here. Okay. So now they're kind of on the same metric. Which brings me to, real quick, I need to now bring up another Shiny app. This is something that used to be in, I used to do this in the data visualization lecture, but I figured it fit better with the z-scores. So this notion of, and I got to really quick before you see me do anything. I should have set this up ahead of time, but here we go. Okay. So this is, if you're in the finance world, this is kind of a common figure that finance people like to use, which is what's called a dual scales chart. So what we're looking at here is two lines, right? The green line represents the trade index volume between the United States and New Zealand up through 2017. The red line represents the New Zealand US dollar exchange rate. Okay. And obviously the x-axis is time, but for me, as we said, I have one absolute in life, right? The probability of using a pie chart is 0. That's the only probability of an event that should be 0. The probability of using a dual scale chart is pretty close to 0, but not 0. And I'll explain under what circumstance I think it's okay to use it. When people have these plots, really what they're interested in is what's the relationship between exchange rate and the trade volume. In which case, I say, this is the plot you should have, right? If I show a scatter plot, it clearly shows there's a relationship here. The problem I have with the dual scales is like if I pick any point, like right here at this intersection, what is this value? So this is obviously 1992, but is it zero point 0.5 or is it, 90, right? So that's the problem I have is the y axis is ambiguous because you've got two different meanings to it. And what this Shiny app is trying to show is like I as a graphic designer can change the range of the y-axis such that I could potentially, you know, if I showed this and I published this, I might be able to make the argument, yeah, there's no what do I have? The red line, the exchange rate is very volatile, but the trade volume is pretty constant, right? So the relationship is weak. But if I look at the scatter plot, it's clearly strong, right? We haven't talked about correlation. The correlation is 0.88. That's huge, right? So my problem with dual scales is I could potentially manipulate it in a way to change the narrative of what the data really says. Okay, so what's my solution? So if you want to do it, you could do this set as default. So the default is actually converting each of these to a z-score. Okay, so now the y-axis is a z-score, and if you want, you can label it, right. So right here I say z-score equals 0. US the exchange rate is 0.63 and the trade volume is 65.77, right? 0.63 is the mean exchange rate and 65.77 is the mean trade volume, right? And then I can go one standard deviation, two standard deviation above and below. So if you find yourself in a situation where someone asks you, your boss says, I want both these things and there are different metrics and you're going to put them on the same kind of scatter or plot like this. So my advice, convert them to z-scores first. Okay, there's my soapbox and I'll stop there. Uh, what's that? Tell that. What am I telling Hadley? I missed that. Oh, by the way, doing this in ggplot is really hard. He made it deliberately difficult to do dual scale charts. So if you're so interested, you can go look at the R code and see how I managed to do it. I forgot I wrote this years ago, but I do remember it being a real challenge to make this plot work. I think I had to actually do scale translations and then manually add a second axis label. So, anyways, yeah, you shouldn't do it. But when you do the z-score, it's trivial, right? Because it's the same thing. And all I did is change the y labels to make them fit. Oh, is this he probably railing on it? Um, yeah, look at this. Thank you, Masood. That's great that you have that there. You notice pie charts are also hard to create in ggplot. Also not by accident. Okay, normal distributions. As I said, it's not a single distribution, it's a class. What is true about normal distributions is that 68, 95, 99, as you go 1, 2, and 3 standard deviations around the mean, wherever that mean is, and whatever your standard deviation is going to be true. So here, this green line, so you got to be careful, right? So if you just plot things in R and you just let it use the default, axis range, right? These look like the same thing. But when you plot them together, you could see, well, we can have skinny and tall normal distributions. We can have wide and short normal distributions, right? They come in all shapes, right? But they all that still have that 68, 95, 99% rule. All right, so let's see here. I'm just gonna go over that because we already talked that. Okay, this week's lab, one of the things you're gonna do is like because in order to leverage these properties of the normal distribution, we need to ensure what we have, what we're measuring, what our variable is indeed following the normal distribution, right? So here's a simple data set with the height of 100 males. Okay. And we want to leverage the normal distribution. And so here, first thing you do is, at least what I do is plot a histogram. Does it look normal? Ah, pretty good. We talked a little bit about the issues of histograms and picking bin widths. And okay, so, well, let me superimpose a normal distribution on top of it, a theoretically perfect normal with the mean and with this mean and standard deviation. Okay, yeah, that helps. But what you're going to play with this week is the quantile plot. And what that's going to do is convert your measurements into theoretical quantiles. Assuming it fits a perfectly normal distribution, things should spread out in the way that they would in a normal distribution. So when you plot it on the x-axis, you're getting the theoretical quantile, right? So you have a mean of 0, 1, 2 standard deviations above and below, and then you have the raw metric. And then we could superimpose this unit line. And so what you're looking for is if it's perfectly normal, all the lines will fit exactly on that line. Okay. That almost never happens. So what we're looking for is it close enough. Now, one thing that this reveals to me is like we got this kind of step, and that's an artifact because this data set measured the heights in whole inches. But when you go to quantile, you're going to get the fractional, right? So each of these gaps is 1 inch because we didn't do fractional inches. Okay, great. So this might be okay. Now, when you have these are just some examples. Like when you have right skewed distributions, you tend to get like this curve up, left skewed would curve down. You can get short and long tails, right? Which is going to show a little bit of skewness. So it's not perfect, but it's a pretty good tool. And what you're going to work with is this QQ norm sim to provide another layer of like reference, if you will. And so the way this works is this top left, this plot is the actual data. That's the same as this, right? And then the other 8 panels are going to draw a random sample from the normal distribution. So it's using the R norm function with the same mean and standard deviation, and it's going to plot those. And so what you're looking for is like, this looks pretty good, but like, what are these points on the edge? And then I see something like this is like, whoo, this should be from a normal distribution and it looks worse than what I have, right? That's the judgment you're making. Now, what I will say is quantile plots work really well when you're within the 2 standard deviations. When you get beyond that, there's often not enough observations, and small increment changes can result in things like this. So in a lot of ways, I kind of often ignore it if I get points when I'm either below -2 or above -2 or above +2, and the points fall off the line. That generally doesn't worry me too much, and it's not like an indication that there's a big problem. Now, if it's far off, right, it's clearly an outlier, but you probably would have already detected it if you did a box plot, for example. That would be a way, or it's going to be obvious. You're going to look at it and it's like, oh, well, what's that point way out on the right or left? So this is kind of trying to get a sense of that shape in the middle, right? Is that kind of fitting that normal distribution? Okay. Next, I want to talk about this. So this is when we're going to talk about Milgram, because it's kind of an interesting data set that actually occurs somewhat frequently. And this also gives me sort of a small opportunity to talk about ethics in data science, which I think is desperately needed now, even more so in the last 2 years. So if you don't know about Milgram's experiment, this is often taught in like Psych 101 classes. It's interesting, right? Because what Milgram was trying to do is figure out how the Holocaust could occur, right? He was trying to understand in Nazi Germany how so many people blindly followed orders to do some pretty you know, terrible things, right? So, I mean, his goals, I think, are laudable, right? He was trying to understand this thing about, human psyche. And so he devised this experiment where he recruited participants, mostly undergraduate students, who were in the role of the teacher. The experimenter and learner were in on the study. They knew what was going on. And so the experimenter told the teacher who was recruited, says, you're going to teach this learner, these tasks. And when the learner gets the task wrong, you're going to administer an electrical shock. And each time they got an answer wrong, the severity of the electrical shock would increase. Okay. And so basically, Milgram wanted to see how far would people go before they said, wait a minute, I'm not going to do it. Now, there was no electrical shocks administered. The learner was acting, and they did act, and you can find videos of this on YouTube. The experimenter's there, so when the teacher starts to hesitate, the experimenter is like, no, you agreed to do this. The learner agreed to this is part of this, et cetera, right? To see if they would follow the orders, right? Okay. How does this connect to ethics and AI? So, Angela and I are trained social scientists, I think, in a lot of ways. We both have doctorates in educational psychology methodology, strong stats, but we took a lot of psych courses and educational courses. If you don't know this or the Stanford prison experiment, when we do research now, when we do our DAX research, we have to get what's called Institutional Review Board or IRB approval. All research done by academics now that involve human subjects have to go through this process to ensure. And we have Milgram for a large part to thank for that, right? Now, I think it's a good process, but it is laborious. I'm not going to lie. Angela can chime in as the person who manages, who is the lead on most of our IRB applications now. It's really important, but this started because of this, right? And social scientists and human subject researchers kind of had this moment of like, okay, as a field, we need to do better, right? And I think physicists did the same thing, right? Oppenheimer, I think, was very distraught after World War II and how the atomic bomb was used. And now physicists consider their work before that, how could this research be used for good and harm and right? And I don't think as data scientists, we're asking that question right now. And in fact, the leaders like Sam Altman and the like absolutely are not asking this question at all. And we're seeing, I think, some pretty, bad uses of statistics and data science and large language models or whatever you want to call it. That if we as a community don't start to say, should we be doing this, then governments are going to start enforcing things and they're going to probably be more strict, particularly the European Union. So, anyways, if you want more in terms of like AI stuff, maybe Angela, can you find a link to the Stochastic Parrots paper? That to me is the starting place for this conversation. Now, anyways, I'm not going to say any more about AI tonight, but I could say more. I think it's an interesting thing. It is all probability and fairly sophisticated, so it's neat. But we are human beings doing things that are, anyways. We should be careful. All right. So what did Milgram find out? Well, 65% of people would have given a shock that would have been lethal, right? 65% of people obeyed the experimenter to the end. So our success rate here is 35%, right? But this kind of study, right, describes something called a Bernoulli sequence, right? So we could think of each of these people as a trial, right? And I could use a more benign example. We could think of like each person who visits a website, do they click on a ad or not, right? If you want to go the advertising, right? That would be a Bernoulli trial, right? So this is something that happens all the time. Are you going to do this or not? We get enough data and we can kind of have this measure of success. I'm going to put that in quotes. Success is really success here, but sometimes it's just 0, 1. Which one's 0? Which one's 1, right? So if I don't always mean success and failure in that way. Thank you, Angela. Everyone in this program should. Oh, I am a human. Should read this paper. It is a great paper. Goes into some of the challenges and issues of LLMs, both in terms of environmental impact how they're trained, how they reinforce social biases, et cetera, et cetera. It's not a hard read, but it's an important read. Okay, Bernoulli. So we think of each one's an event, and so we could put these together into a Bernoulli distribution. We can extend that, right? So then the next question, of course, is how long would I have to wait before I got somebody to refuse that electrical shock, right? And so we're going to introduce a new. So we have the normal distribution. Now we can introduce what's called the geometric distribution. We think of the geometric distribution as a wait time, right? Do I still have my app running? I do. So if we go to the geometric distribution, uh-oh, that one's not working. Okay, I'll fix that in a minute, or later. Um, right. So is sort of a distribution of wait time. Now, what we'll see is the geometric distribution is going to be bounded at zero. We can't have anything less than zero. So we'll start having distributions that end at zero and then go to positive infinity. So they're not all going to be symmetrical, and they're all not going to be, going both to negative infinity to infinity. So if we want to see, how long does it take, what's the like probability of the third person refusing, right? So we could write that out, right? We need the failure on the first event, failure on the second event, success on the third event. We multiply that out. So the probability of the third person refusing in a shock is about 15%. But what if we want to extend this, right? So the geometric distribution describes the wait time for independent and identically distributed Bernoulli random variables, right? Meaning each event has the same probability of success, which we've estimated to be about 35% in this example. And so then the probability failure is 1 minus that. So we can kind of generalize if we think about this, right? So if we're looking the third person, we going to have 3 minus 1 failures and 1 success, right? So we're taking, so if we wanted 3 minus 1 was 2 failures and then 1 success, right? So that's sort of just generalizing what we did on this slide. So now we could say, what's the likelihood of the 10th person refusing? Well, we would take the probability of failure raised to 9 times the probability of success. Okay. So now we have this distribution. Really, what we're probably more interested in is what's the average wait time? Well, the average wait time from a geometric distribution is defined as 1 over p. So in our example, right, the average wait time is 2.86, right? We can't have fractional people, so we'd probably say we need at least 3 trials before we get at least one success, okay? And so if we have a mean, we of course have a standard deviation, which is really so square root. So the variance is the inner part, and then we take the square root to get the standard deviation. So we have the ratio of failure to success squared. Okay. And so in this case, we get a standard deviation of 2.3. So what we would say is we need to test 2.86, give or take 2.3 people. So probably wouldn't be surprised if you did 3 trials, maybe you wouldn't get a success. But once you get to 5, right, then it starts to be like, I should have gotten a success by now. All right, so that's just like kind of that wait time. But let's extend this a little bit more. Now we're kind of interested in like, well, we have 4 people and we want exactly 1 success. And so we have 4 people, so we could write this out, right? This is a simple enough one we could write out. So we could have person A refuse and then everybody else shock, and then person B, et cetera, et cetera. We go through. So the probability of person A shocking is about 9%. Person B, of course, they're all going to be the same, and we can add that up. So out of 4 trials, getting exactly 1 person to refuse the shock is about 38%. So this describes what we call the binomial distribution, right? Which is the probability of so many successes in so many trials. And this comes up all the time in data science. And this is going to be, we're going to see this again when we talk about logistic regression. We want to do predictive modeling with a 0-1 outcome. right? This is used from everything, like I said, advertising to understanding, you know, why the Holocaust occurred, right? Or how that one part of it at least, right? And so what we were doing here is just generalizing a little bit, right? If we went back here in the geometric, that's our wait time. How long do we have to go before we get a success? The binomial is going to say, well, what's the likelihood of getting this many successes in those trials? So here where we raised it to n minus 1, so we just need to generalize this a little bit. So we're going to say, well, how many successes do we want? So k represents the number of successes. So in this example, it was 1, but it could be 2. So if we wanted 2 successes and we're doing 4 trials, then we want 2 successes, 2 failures, right? And so that's all we're doing here is generalizing those those probability multiplications. There's a small little digression because it's like, okay, great. How many, trials or how many outcomes does that mean, right? So when we have 1 success in 4 trials, we can write that out. But what if I say I want 3 successes in 10 trials? Whew, that gets really complicated, right? So we have to use this choose function. If you don't remember, the explanation point here is a factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So you're taking whatever that number is, multiplying it by each integer down to 1. Anyways, so if you want um, uh, 10, 2 successes in 9 trials, right? We could substitute that in. So how many combinations are there? How many ways should I need to write that out? Well, if I do that, there's actually 36, right? Where when we had 1 success in 4 trials, we had 4, right? We'd have to figure out all 36 combinations where we have 9 columns, right? And you have 2, right? That would be pretty tedious. Now, you don't need to memorize this formula at all. You won't even really use the choose function, although it's there for you in R if you're going to do this by hand, because what you're going to end up using is a binomial function, right? So we take this product of the success and failures times the number of trials that occurs, right? Why are we doing that? So in this case, right, we just added these 4 times. We took this, this, and we essentially multiplied it by 4, right? So that's why we need to have this bit here. So we have those successive. So this is giving us, in this example, what the probability for 1 row, and we need to know how many of those kind of combinations. So that's why we need to do this. Okay. So, but in practice, what we're going to end up using is just the binomial distribution. So going back, if we had 4 trials and we say the probability of success, so we're going to use the D binom in this case, right? Because I want the density. Now, the binomial distribution is a discrete distribution, meaning it only has values at the integers, right? It doesn't, their fractions don't work, which makes sense because we're counting things here, right? Unlike the normal distribution has fractional values, right? So going back to what we talked about, I think last week, discrete versus continuous random variables, binomial is a discrete distribution. So in this case, not only can I say, well, I want 1 success in 4 trials or 2 successes, I can do them all. And so the first parameter is I'm saying, give me 0, 1, 2. I want 0 successes, 1, 2, 3, 4, all the way up to 4. And so this is the full binomial distribution, right? So the probability, right? So our question before is, well, what's the probability of getting 1 success in 4 trials? Well, it's 38%, right? The probability of getting no successes is, I don't know what that is, 18-ish percent, right? We could see the probability of 2, 3, and 4 is extremely unlikely, right? Getting 4 successes when a probability of success is that. So the binomial distribution, my app works, right? I can do this one. Doing things live, right? So we have our, size. So we were doing 4 here. Probability of success is 0.35, right? So we can read those out, and well, once we get to 4, this 10, I should probably make this 4 as well, right? So this is the full, distribution. But like I said, if we wanted to go to 10 trials, right, we can kind of see the probability of once, this would be the probability of exactly one. But like the normal distribution, we could say we could say at least one, right? In that case, I would use the p norm, right, which is going to give me this area. But if I want more than one, I would take one minus, right? So we can kind of combine this. Now, if you're in the marketing world or salespeople, right, this is used all the time. What's the probability of somebody clicking my ad? How long do I have to show an ad before somebody clicks it, right? So we use a geometric to say how long do I have to wait, or if you just want to know what's the probability of getting this number of people to kind of engage, you've done some prior data and said it's, X percent. So now you can do that and you can say, well, what needs this is really useful. You need to figure out your ad spend, right? In order to get response and calculate that out. All right. This is another Shiny app written by my colleague, which allows us so you could see the binomial distribution is not symmetrical at all, right? So as the probability gets smaller, right, it's going to kind of skew to the left. As the probability gets higher, it's going to skew to the right. Let's go. Let's actually make this like 100 might be too much, right? So you could kind of see it will skew as we go from away from. But if we're at zero point 0.5, it is going to be fairly symmetrical. Does not follow the same rules as the normal distribution, by the way. So be careful of that, right? We can't talk about standard deviations above or below, but um, this is another way to kind of see. So when we get to like more, we'll see when we get to logistic regression, which is leveraging the binomial distribution. When we talk about predicting rare events, some of this will come out because there's often not enough occurrences out there and it becomes really, really, really challenging. All right, here's our 1 minute paper. I'll throw the link in the chat. Happy to entertain questions. Which one was not geometric wasn't working? For invalid first argument. Yeah, okay. So I got some more testing to do. Some of these I don't even know what they are. I just went through our documentation to find all the distributions. I think I'm going to add this link to my dual scales slide. No questions? All right. Well, then have a great week, and we'll see you next week.
Thank you.